All right, let's talk about how to go about doing the different chemical naming examples on here, both in terms of giving the name for a formula or give a formula for the name. So first of all, everything's here, which means the first and biggest issue you're going to come up with or run into is using the right rules for either naming this formula or giving a formula for the name. So in order to do any of these, the first thing you must do is decide which rules apply. So we're going to label each with A for acid. Let's see, I for ionic, and M for molecular, because those are essentially the three systems that we need to use for these things. And each one has its own details, but we need to identify all of these first. So we look here, metal. Remember that I should say acids generally start with H, as in like there's an acid. And there's another acid. There's another acid. And there's another acid. Okay, your acids start with H. All right, what about your ionic compounds? Ionic compounds are either a metal and a nonmetal, such as this right here, ionic compound. Right, there's another ionic compound, metal, nonmetal. There's another ionic compound, metal and a nonmetal. Or sometimes you can have, and I don't think I've seen examples here, where you have, there's no metals present, but you might have a polyatomic ion. I don't see any of those. But an example would be like NH4Cl. This is ionic because even though there's no metal and nonmetal, it contains a polyatomic ion, therefore it's ionic. By the way, this would be called ammonium chloride. Anyway, so let's just go through and label all the rest that are ionic. Metal and nonmetal, metal and, metal and nonmetal. So that's ionic. Molecular is basically nonmetals only with no polyatomic ions present. So nonmetals only with no polyatomic ions, nonmetals only with no polyatomic ions. That's a metal and a nonmetal. Oops, missed that one earlier. There's your ionic. Metal and nonmetal, or sorry, the nonmetal and nonmetal, they're both nonmetals. So molecular, both nonmetals, molecular, both nonmetals, molecular. And again, they're nonmetals and they don't contain any polyatomic ions. So there, I've classified all of them. That tells me what rules to use. So let's use the ionic rules, which means, okay, sodium is a group 1 element here where we know it's a +1. So because it's a +1, don't need a Roman numeral. Sodium carbonate. How did I know to call it carbonate? Because I see this CO3 and I find CO3 right there. It is carbonate. Okay, let's go through all the these one at a time. I think maybe I'll do all the ionic ones first. Iron and a sulfate. So iron and a sulfate. Well, iron is something, if I ask you the charge of iron, you don't know because it's a transition metal with variable charge. So I have to figure out what the charge of iron is in this iron sulfate. So I look at the list of polyatomic ions because that's sulfate right there. And finding sulfate, I see it's a -2 charge. So I say, look, the sulfate's a -2, therefore the iron must be a +2. So I'm going to call it iron, Roman numeral 2, sulfate. Aluminum is known to be a +3, so no Roman numeral needed. Aluminum chloride. Cobalt is a transition metal whose charge is unknown. So we say, look, it's attached to 2 bromines. Each bromine's a -1. There's 2 bromines, so that's a total -2 charge. The cobalt must therefore be a +2, because however much minus charge there is, there must be equal amount of plus charge. So cobalt, Roman numeral 2, bromide. Let's skip on to the next ionic one. Strontium phosphate. Strontium is known to be a +2, so I don't need any Roman numerals. Strontium phosphate. Let's see, next ionic one here. Silver hydroxide. Silver is known to be a +1. Yes, it's a transition metal, but you have to memorize it's a +1. So if you know it's a +1, then no Roman numeral needed. Why did I not call it silver oxygen hydride or something like that? Because hydroxide is right there. So you have to recognize it as hydroxide. All right, that's the ionic ones. Let's do the acids, because that's next. Acids, okay, so that's, where is it? Here we go. Oxalate. And we always say if you ate an acid, you would say ick. So oxal, and the 8 instead of 8, I'm going to say ick. Oxalic acid, because of the H at the beginning. Let's skip to the next acid. Sulfite. The ITE, this takes the us ending. Sulfurous acid. Let's see, next acid, H2CO3, that's carbonate. If you ate an acid, you'd say ick, so it's going to have ick in the name. Carbonic acid. Let's see, acid, here we go. There's no oxygen in the formula, so the name starts with hydro. And it's bromine, so bromic. And it's an acid, so acid. Hydrobromic acid. All right, that's all the acids. Now for the molecular ones. You have to memorize this one. Yes, technically you call it nitrogen trihydride, but this is a special one. You have to memorize it's ammonia. Non-standard name. Here, silicon, because you never use mono if there's just one of the first one. You only use mono if there's one of the second one. So silicon dioxide. These Greek prefixes such as mono or di or tri are only for the molecular ones. Okay, let's see. Diboron tetrahydride. Carbon monoxide. Remember, use mono for the second one, but never use mono for the first one. And if there's more than one of the first one, then you have to use whatever the appropriate root word is, like di for this boron right here. Okay, diphosphorus pentoxide. Technically, penta is the root word, but for whatever reason you drop the A. So by the way, had it been P2H, or let's say F5, that would have been diphosphorus pentafluoride. So for whatever reason with oxygen you drop that A, but for the non-oxygen ones keep it there. Pentafluoride, not pentfluoride. All right, same thing here. In order to correctly give the formula, you need to make sure you know what you're dealing with, though this is a little clearer in that the acids all have acid in the name, and you should recognize right away if there's any Greek prefixes anywhere, you will be dealing with a molecular compound. So it's a matter of just taking the name and writing what you see. So for the non-ionic things, it's probably the most easy. Dinitrogen trioxide, so dinitrogen trioxide. Acetic acid, you just look up acetic acid, you just recognize acetic. What is that? And then you go look on here, acetic, oh, that looks like this one right here. Acetate, you go look up this one, and you just pair up, add however many hydrogens necessary to match up with this. So hydrogen is a +1. If this is a -1, you only need one hydrogen. So the way you'd write it is H at the beginning, and then the acetate formula. C2H3O2. And that's fine. Hexanitrogen heptabromide. So there's your nitrogen, there's your bromine. Hexanitrogen heptabromide. It's not showing up well, but yeah, 6 and a 7. Nitrous acid. Okay. We find which one of these? Well, you have to remember, if you ate an acid, you would say ick. So ick, if an acid has ick in the name, it's an ate. If it has us in the name, it's an ite. So this is nitrite. So it's NO2. And because it has a 1- charge, it's only going to have one hydrogen, HNO2. Methane, that's just one to memorize, CH4. Lithium acetate. Let's see, so that would be, how do you get that? That's lithium. Well, first of all, I should recognize this is ionic. There's no Greek root words, and the word acid is not there, so this is ionic. There's lithium with the 1+ charge. C2H3O2 is the formula in charge according to what you see on the list. There's acetate right there. So you just have to figure, okay, switch the charges, 1 acetate, 1 lithium, LiC2H3O2. And that works. Phosphorus octafluoride, phosphorus octafluoride. Iron trioxide, that's iron with a 3+ charge, and oxygen, which you look up on the periodic table as being a -2. So that's 2 irons and 3 oxygens, so Fe2O3. Maybe we'll even box that to make it stand out. All right, aluminum hydroxide, so that's aluminum, the 3+ charge. I recognize it as ionic because there's no Greek prefixes and the word acid isn't there. And I look up hydroxide right here, OH with a -1 charge, so that's OH minus. So the formula has 1 aluminum and 3 hydroxides. So there's your aluminum, there's your hydroxide, and because there's more than one, I have to put parentheses around the polyatomic ion and a number of how many there are. No parentheses here is necessary because there's only one of this polyatomic ion, 1 acetate. Here there's 3 of these hydroxide units. Here, zinc sulfide. Zinc, you have to memorize it's a 2+. Sulfur is a 2-. Switch the charges, 2 zincs, 2 sulfurs, so Zn2S2, and reduce that. A 2-to-2 ratio is the same as a 1-to-1, so ZnS for your answer. Hydrofluoric acid, or sorry, hydrochloric acid. Hydro means there's no oxygen in the formula. So that's just, it's an acid starts with H, and then hydrochloric acid means that, HCl. That's it. Silicon tetrafluoride. Silicon, oops, I don't know why I put H, or I don't know why I put that O there. But tetra means 4, so tetrafluoride. Hydrophosphoric acid, that means no oxygen in the formula. So hydrophosphoric acid means phosphorus, which is a -3. Hydrogen is a +1. So that means the formula has 3 hydrogen, 1 phosphorus, for H3P as the formula of hydrophosphoric acid. Unlike phosphoric acid, which is ick, means it's 8, so that the polyatomic ion ends with 8. Phosphate, there it is, phosphate. So that's PO4 with a 3- charge, and H is a 1+ charge, so I've got 1 phosphate and 3 hydrogens, so H3PO4 is phosphoric acid. Finally, silver bromate. Silver is Ag+. Bromate is on your list of polyatomic ions. There it is. BrO3 with a - charge. BrO3 with a - charge. So your formula has 1 silver and 1 bromate. So AgBrO3, no parentheses needed because there's only 1 of each. And there you go. So that's a quick overview of how this works. I'll just put everything here so you can see it all in one place. There's go through 13. There's the rest of the front side. And there's the back side all in one place. All right, there you have it. Happy studies.